Yes. All right, cool. All right, so my name is Mike. I am a developer advocate at a company called Sysdig. And Sysdig, our founder was the one of the original authors of Falco, or the original author. And so Falco is deeply tied to sort of Sysdig, and Sysdig is tied to Falco. But we're not going to really be talking about any of Sysdig's commercial products today. We're just talking about the open source stuff. But I mentioned Sysdig because that's where I work. Before coming to work at Sysdig earlier this year, I was at Google. Before that, I was at AWS. Before AWS, I was at Docker. So I've been doing, containers and Kubernetes and cloud native stuff since about 2015. And having worked for, Docker, AWS, and Google, have spent a good amount of time at some of the companies that kind of lead in that space. So we're going to talk a little bit today about sort of the history of, cloud threat detection and cloud evolution. And then that'll set the context for what Falco does. We'll talk about Falco. We'll do a couple labs, and then we'll wrap up with a discussion on Falco's ecosystem and how that all comes together. And then we'll close it down with some remarks. We will have, this is about 2 hours for this workshop. It goes anywhere from 90 minutes to 2 hours, depending on questions and what have you. Be sure to put your questions in the chat. I'll be checking them as I'm able. And we will have 3 hands-on labs. I will give you a link to the lab guide when we get there, because I know not everybody will be able to do the labs. I'll run through them myself, and you can run through them along with me. And then I'll give you a few minutes to finish up after I'm done talking, and then we'll reconvene. So you'll have 3 labs, which will essentially also serve as 3 breaks during the 2 hours. So if you need to get coffee or whatever, tea, whatever it is, you'll have time to do that. So let's jump right into it. So I actually didn't mention this, but before I was at AWS and everywhere else I talked about, I actually was at VMware. And before that, I was at Intel, right? And so this actually slide takes me back to my Intel days, where I worked on managing systems for Intel's, campuses here in Oregon, in the United States, Oregon. And we would buy servers, and even though we worked for Intel and we made servers, it would still take us months to get them, right? We would order them up. It'd take us months to get them. Then we would have to configure them, and we kept them under desks, and we kept them in like supply closets. And whenever one went down, we were supposed to copy all the settings and write them in this book so that we could replicate the servers if we had to, but we couldn't really do that. We could, we just didn't, because it was too complicated and too difficult. So whenever one died, whenever a server died, I would literally be like, oh my gosh, what did I have on this server? Go to the backups, restore the backups, hope they were all taken care of. So the reality, and that's the other thing too, right, was every server kind of did its own thing. We couldn't mix the servers, right? So our file server was not the same thing as our database server, and not the same thing as our application server, right? Everything was installed onto one physical box, like one box, one task, which led to incredibly low utilization. Obviously, this was a while ago, but these practices still exist today for people managing data centers. Certainly, I didn't mention this. I spent some time at Puppet. Certainly, there are tools like Puppet and Ansible and Chef that came along to sort of try to help you automate some of this stuff, and being able to replicate and manage servers and deal with configuration drift. But that didn't deal with the deployment time lag and the utilization problem. That was solved by VMware, right? So what VMware did was took the ability to say, okay, well, instead of having this server over here with an operating system and all the middleware and all the apps, let's encapsulate all of those software components into one blob, and we'll virtualize away all the hardware, right? So we'll use a hypervisor running on the physical server that will allow us to instantiate multiple virtual servers, multiple virtual machines. So my database server on the left and my application server on the right in my diagram represent full stacks, right? They have their own kernel, their own operating system, their own dependencies, their own applications. That's because we still couldn't commingle applications, right? The conflicts between libraries and DLLs and all of that stuff prohibited it. But now we were able to take 3 physical servers running web database and maybe an app front end, or a application middleware database and a web front end, and we could put those maybe onto a single server, right? And we could now get rid of 2 physical servers. We saved on real estate in our data centers, and all of a sudden people could start deploying servers. Here it said days, but if you had the physical hardware, you could get new servers up in hours, and you could bring servers up and bring servers down. It was great, right? But you still sort of had this like tight coupling between the application and the kernel, right? And so we weren't really changing the way we did anything at this point, right? The thing that changed was, how do we deploy these systems? How do we get them into production? But once they were in production, we were patching our virtual machines the same way we patched our physical servers. We were updating our apps the same way, right? We were definitely still in the space where we're treating servers as sort of these individual units that could mutate and change over time, right? And could certainly get better utilization. We could deploy things faster, but we had not evolved our processes really beyond deploying virtual machines versus booting off of golden images and installing software that way. So then around 2014, Solomon Hykes and Docker Solomon Hykes shows Docker for the first time, and that brings in the modern era of containers. And there's always somebody who says, well, containers aren't new, they've been around for a long time, and they have. Containers are based on some features in the Linux operating system, namespaces, C groups, change root. These utilities and features allow us to construct these isolated Linux processes and Windows. I'm talking, I'll say Linux, but for containers, it's all basically the same. It all runs on Windows too. But these processes now are sort of this all-encompassing, atomic unit for an application. And if you go back to virtualization and you say, well, virtualization was designed to solve the problem of hardware utilization, right? That really was the fundamental problem that virtual servers solved, right? The ability to run multiple workloads on the same physical hardware without conflict. And so that is, that's what virtualization did. What containers solved was, it doesn't work on my machine, because they were inherently portable, right? And so, previously, if I was a software developer and I'd write some code, I'd send it over to you, maybe you're doing a code review on it, or maybe you're in the QA department and you're going to test it, and it works for you, and then we hand it off and we go to put it into production and it doesn't run. And so somewhere between my desktop and the test environment and the production environment, something changed. There's a different version of libgcc, or there's a different, there's the conflicting libraries, or somebody made a manual change on the server and didn't tell anybody, and now my new version doesn't work. Containers were designed to solve that problem. So with a container, I know that if I deploy my application into a container, you can run it on your desktop, you can run it on your server, in the cloud, on bare metal, on VMware, wherever you want to run it. And it's always going to run the same, because everything it needs to run is packaged up in the container image, right? And because these container images all share the kernel of the underlying operating system, they're incredibly lightweight, super fast to boot, much smaller typically than a full-blown virtual machine, because they don't have their own copy of the operating system, their own copy of the kernel. They have operating system functionality, but usually it's pared down to just what you need. So you have this portable execution environment that's super lightweight, that can move across everywhere. Now, this is where we start fundamentally changing not only the way that we deploy software, but the way we write software. Because now we can go in and we can start writing code in what's called microservices. And so what microservices let us do is they let us write different aspects of the application and separate all the components. So if you had a e-commerce app, you could say, okay, well, I'm gonna have a login service, I'm gonna have a catalog lookup service, I'm gonna have a catalog update service, I'm gonna have a payment service, right? And all these different components, and they could all be written independently, and they could all be written in whatever language made the most sense for that particular piece of discipline, right? That particular piece of code. So these loosely coupled, you know, fine-grained in the terms of what they could execute, units of code, right? And they could be shared across applications. So now if you had an application that needed, 3 different applications that need a login service, you could use the same microservice across those 3 applications if you wanted to. But it also meant that you were deploying vastly more components. So you went from having this virtual machine where everything was in one VM potentially, and now you've got 10 containers make up this application, and we're scaling them independently, right? And so now I want to have the web front end, I want it to have 100 copies, and the middleware needs to scale, and I've got a database running somewhere that's sharded, and I'm accessing that. Well, everything is just proliferating, right? It's all getting very complicated. So we start seeing the need for software that orchestrates all that. And that's where Kubernetes comes in. So Docker had Swarm, Kubernetes came out of Google. And the job of Kubernetes in all of this is, at the most basic level, Kubernetes is a very complex piece of software, but at the most basic level, it was really about, how do I tell a system what I want and then have the system just worry about that for me? So it's called declarative, right? We're going to declare what we want. I want 10 copies of the web front end. Okay. So I go out and Kubernetes goes, here's that container image. I'm going to launch that. I'm going to scale it out to 10 instances. Oh, that one died. I'm going to bring another one up in its place, right? And that helped us manage the proliferation of all these different application components, and made it, much easier to scale and deploy things. So let's see here. Okay. Just want to make sure there was nothing in the chat there. I saw a couple notifications, but we're good. Okay. So Kubernetes was founded by Google, but it was donated to the Cloud Native Computing Foundation. And the Cloud Native Computing Foundation was founded in 2015, and it exists basically to ensure that projects for cloud native workloads all sort of adhere to a basic level of, it's not actually basic, it's a pretty high bar for, quality and documentation. And it also ensures that no one company owns that technology, even though it's open source. So we've seen some companies over the last few years say, oh, this is an open source product, but then when it starts getting adopted in the market, they maybe go and change the licensing agreement. By donating Kubernetes to Cloud Native Computing Foundation, Google assured that that would never happen. Google still works on the technology, as does AWS, as does Red Hat, as does hundreds of independent developers, but the licensing and the stewardship is all managed by the Cloud Native Computing Foundation. And these projects come in and they have like a sandbox level, which is, hey, these are kind of new, cool technology. They have an incubated level, which is, okay, these are like release candidates. They just need a little polish. And then they have a graduated level. And I mentioned this because Falco is a Cloud Native Computing Foundation project, and it is at the incubation level, although we've applied for graduation, and we're hopeful that that's going to get sorted out pretty quick. Anyway, so I use the term cloud native. What does that mean? So I talked a lot about the technology. I talked a little bit about the processes, but cloud native is really this idea of marrying those two things. So containers and Kubernetes are modern tools, but modern techniques include things like continuous integration and continuous deployment, GitOps, infrastructure as code, all of these tools that help us define our environments in software and to track them in version control and being able to do things rapidly and be able to recover quickly from failures. It's also a mentality around how you build applications, right? We build applications assuming they're going to fail, right? Because we have systems to help deal with that redundancy. We use circuit breakers, we use backoffs, we use retries, these sort of things to help develop modern software that can be deployed across various environments. It's called cloud native, but the reality is that it may run in the cloud, it may run in your data center on VMware or Hyper-V or some other virtualization platform, or it may run in your data center on bare metal. All of those things, it can run, it doesn't have to be in a public cloud, it can be a private cloud, but the idea is that you're building applications that are designed to recover from failure. You're building, they're highly scalable, they're flexible, they're deployed and managed with modern tools. A lot of that are all based on these principles of sort of like, do as much stuff as you can in code, make it replicatable, make it easily version controlled so you can roll back. So that's sort of what cloud native is. And that evolution is important because because the evolution from the data center to the cloud and the way applications were architected, delivered, and managed is parallel. The security implications parallel that same path, right? So now if we go back again to my time at Intel, right, many years ago, when someone said, oh, what's your, you have security, what is that? Well, we have a firewall, right? We have a line coming in from the internet, and we've got this firewall, and we know that everything, we're going to stop bad actors before they come in. And if we see that somebody got through the firewall, we're going to know there was a problem, right? So firewalls were how we thought about security in the data center, and firewalls and virus scanners were how we thought about them on the desktop, right? And that's great when you operate an enterprise and you say, or even a small and medium business, and you say, okay, all my stuff is, it's in this environment, right? It's in my data center. It's behind this T1 line or this whatever, fiber optic connection to the internet. And I know there's one way in and there's one way out, and it's easy for me to control that. But now we're in the cloud, right? And there isn't a perimeter and lines, and maybe some of your workload is on Google Cloud and some of it's on Azure and some of it's on AWS. Excuse me. And these things need to talk to each other. If you've not done this, do it just for a little while. Go up on any cloud provider of choice, DigitalOcean, Azure, AWS, Oracle, whatever, whatever you want it to be. Spin up a virtual machine instance with a public facing IP address, and then put some software on there to monitor the connections or look at the logs and realize how quickly that system starts being essentially attacked. People out there constantly scanning known public IP ranges for cloud providers, looking for systems that have been deployed with public IPs to find weaknesses, right? And we are putting systems on the internet every single day, right? And we're doing this, if you think about IoT, you think about public facing cloud servers, all of that stuff. It's all exposed to the outside world. And there are multiple layers of security now, right? Before we talked about, oh, there's a firewall. Well, now there's a firewall, and there's a virtual private network, and there are IAM roles, identity and access management roles. There are, all these different layers that go into it. So you can't just think about security at one level. And now you've got, software itself from, in the last 2 decades has just become super broad, right? Companies that you would never thought of as software companies are software companies. John Deere in the United States makes heavy equipment for farming, and they're a software company because they're using AI in their tractors to identify what are weeds and what are crops, and so that they can, spray insecticides on weeds with precision using cameras and cloud servers and all of this information, right? Every company is a software company essentially these days. And that means multiple teams using multiple resources. And how do you divide all that up? And people make mistakes, right? I will admit to a couple of super common mistakes that I know that I'm sure people on the call have made these mistakes. I have committed my AWS secret keys into a public GitHub repository, for instance, right? So I went up there and I put them in there. And just like there's people scanning these virtual machines looking for weaknesses, there's people scanning public GitHub repos looking for AWS_secret key. And if they see that, they look to see if there's a secret key associated with it. People are committing their secrets into public GitHub repositories. I wrote a blog post one time teaching people how to deploy WordPress on AWS. And as part of that, I talked about how to deploy this plugin to sort of federate your static images across multiple cloud distribution network endpoints. And I was using a piece of software for that. And they said, create a service account and give it full permissions to S3. And I said, okay, I'll do that. And then somebody found my tutorial, and this person had 100,000 Twitter followers. And they said, who's the idiot that wrote this tutorial? And I'm like, it's me. I'm the problem. I'm the idiot. It's me. And because I had given way too many permissions to that service account, that the vendor for the plugin said, we need full permissions from S3. But the reality is they didn't. And I figured this out by going through the 43 permissions in S3 and trying them each one by one until I figured out the 6 that were actually needed. Now, why did they say full control? Because it was easier, right? Because when you have 43 different permissions for S3, and S3 is one of 160 services on AWS, you all of a sudden have like 5,000 different permissions you could set. And people are naturally going to go with the easy route, right? And it's not because we're lazy or stupid. It's because we have a lot of work to do. I had a attendee. I did this workshop, and an attendee in the physical, in an in-person workshop said, the greatest threat to my environment is somebody is a disgruntled employee because they're already on the inside. And I'm like, that is indeed a legitimate threat. But a bigger threat to your environment is the overworked systems engineer, the overworked, application developer who, because they are harried, because they are busy, they take a shortcut or they make an honest mistake. I did not intend to put my AWS secret credentials on a public GitHub repo. I was just in a hurry and I did it. Right. And that's how it happens 90% of the times. We all know we're not supposed to do that, but we make mistakes. And so that's how we end up. Right. And so what we need is a way to monitor those things to see when weird things are happening. Because before somebody exfiltrates your data, weird things happen in your environment. Right. So how do you detect that? Well, if I build a wall, or if I have an open park, like in the picture, how can I monitor those physical environments in real time? Well, oh geez, I'm skipping all this because I talked about it all. You need a security camera, right? You need a way to look at all of this stuff in real time and be able to say, oh, something weird is happening over there. That person shouldn't be entering that part of the building, or what are those young kids doing back there behind the school? Are they smoking a cigarette? I don't know, right? Security cameras tell you these things, and they send you an alert and they let you know that something's going on, right? And that is what Falco does. Falco is like a security camera for your workload that allows you to look end to end at your environment and see if something is happening that shouldn't be happening, right? So Falco can look at host environments, container environments, service environments. It can look at the way your cloud services are operating. It can look at the way your identity management platforms are operating. It can look at your GitHub to see, is something weird going on, right? So I can have Falco looking at my GitHub, and if it sees that someone has pushed a secret key, it can alert me to that. Or if somebody is running Kubernetes and they started a privileged pod, I can be alerted to that. Now, you should probably never put your secret key in a public GitHub repo, but there are times where you do want to manage, you do want to deploy privileged containers. So it doesn't have to be a known bad thing, but it's a thing that you should know about, right? And that's the thing, is these abnormal, these either operational anti-patterns or just abnormal behavior, right? AWS, is someone trying to log into the console without multi-factor authentication? We can look at CloudTrail logs and we can see that. Okta, is somebody, trying to fake their way through multi-factor authentication? And they just keep trying these random codes to see if they get lucky, right? We can plug into Okta and look at that as well with Falco. So that's, I mentioned Falco. I haven't really told you what it is. I told you what it does a little bit, but let's talk about it right now. So Falco is open source. It's a cloud native computing foundation project. I need to update this slide. Actually, we have over 100 million downloads of Falco now. If you look at combined uses through, just being downloaded, but also it's integrated into platforms from like Hewlett Packard. Enterprise has a cloud protection platform that uses Falco. Sysdig, our commercial project, uses Falco. There's a company called R6. Their commercial product uses Falco as part of their detection engine. So all of these, between all of these deployments of Falco, about 100 million different pulls on the technology, well over 6,000 GitHub stars in there. And basically what Falco does is it takes inputs, it compares them against a rules engine, and then it alerts you if there's suspicious activity, right? The alerts look like this. You'll see these in the lab, but we try to write English language alerts. Well, I mean, they can be localized, but I mean plain language, right? English is my first language, so I say plain English language that says, here's what happened. A shell was spawned in a container with an attached terminal. And we can say the user root did it, what their login ID was, what the container ID was, what was the shell they spawned, what was the command line they run. So we can give you all that information so that you can go back and either do forensics, or you can say, oh, well, that should not happen, or okay, that's a normal thing, right? Again, notice the top one is a notice, the bottom one is a warning. Let's check the chat here real fast. What programming or system language is used to operate Falco? We will look at the rules language here in a bit, so you'll see that. Falco itself, the core components are written in C++, because they're operating pretty deep inside the operating system. So it's largely C++. Things like the plugins and the Sidekick, which we'll talk about later as part of the ecosystem, the plugins can be C++ or they can be Go, right? But the actual language, as an end user, the only thing you ever look at are Falco rules. So there's a rules language, which we'll cover here in a couple slides. So as I mentioned before, Falco can be deployed directly onto a host. So if I had a virtual machine, I could run Falco on that virtual machine. I could run it in a container. I can run it as in Kubernetes as a stateful set that runs and operates. So we can deploy Falco across a wide variety of different scenarios, monitoring cloud workloads, physical workloads, containers, and Kubernetes, all of that. All right, so that is the first bit of lecture, and that is the longest bit of lecture that we go through. So I'm going to give you all 2 minutes to navigate to Falco Workshop, bit.ly, Falco Workshop 1023. You can see that there on your screen. You're going to be asked to input your email, and then you're going to be taken to a screen where you will hit the start button, and then hold right there. But I'll give you guys another minute and a half to do that. And then when that's done, we'll go in and I'll jump into the lab. Thank you, AI Camp. That was very helpful. I should have done that. So yeah, it's in. You can click the link in the lab if you. Hold on, that's not the. Yeah, that is. I just used it. Hold on, I just used it. Bit.ly. Yeah, hold on. Let me go. HTTPS bit.ly Falco. Dang it. Try this one. Yeah, it's got to be capitalized. Yes. Do that one there. Yeah, don't put a capital F. It's weird. It's case sensitive. So use the one that I put in there. Thank you, Hard. Hopefully I said that pretty close to correct. Maybe not. I don't know. Yeah, so try that one. I'll give you guys another minute to get into it. Mine's already up and running. I'll hit the start button down here. Oh, I didn't hit the start button. So, all right. Let me make this a little bit bigger. There you go. Yeah, isn't that nice? I should do the stuff in an incognito window, but what are you going to do? All right, there we go. All right, so we're going to jump into this. The first thing we're going to do is we're going to install Falco, and Falco actually relies in its default mode relies on Linux system calls. And so for the Linux system calls, you want to install the Linux headers for whatever version of Linux you're running. And that's what this uname-r does. It grabs those Linux headers. So we're going to check to see if they're installed. They're not. So we're going to install them. And then once they're installed, we'll check again. And then they are installed right there for 64-bit on x86 symmetric multiprocessor systems. I'm going to clear the screen. So now we've got that. We manage Falco can be installed a bunch of different ways. The easiest way, especially if you're using Kubernetes, is via a Helm chart. And Helm is a package manager for Kubernetes. And the first step we're doing is to make sure that Helm knows where to find the Falco charts. The YAML that describes how to install something in Helm is something called a chart. And so we're setting up, and here's where you find the charts. They're in this repository. And then we'll go ahead and we will install Falco using that chart. So what we did here, real quick, I'll look on the right side of the screen. I'll highlight it over here. The first thing we did is in Kubernetes, there's this concept of a namespace. And a namespace is the way to carve up a single Kubernetes cluster into multiple sort of private areas, right? I think of it, it's almost like a virtual private cloud in AWS. It's almost like that same sort of thing, right? So we created a namespace for Falco, and then we installed Falco into that namespace using Helm. And we said use version 3.6.2, and we said TTY equals true because otherwise the alerts get batched up and it can take a few seconds. We want them to come through in real time. Yeah, so the TTY enables the logs to be emitted without delay. So let's see if this is running yet. Do this. Clear the screen. We'll do kubectl get pods -n Falco. The n Falco is namespace Falco. So, and 2 of 2 are running. So my pods are running. And if I look at the logs for Falco, I can see that everything is open, is running as expected. So there's some stuff in the chat here. Yeah, they will email you the slides. Okay. And then during the break, I'll go and grab it off that slide and paste it in. All right, so now we know Falco is running, right? And so let's go ahead and test it. So what we're going to do is on this machine here on which Kubernetes is running, if I do a kubectl get nodes, my cluster here is just this one node running here. I am going to go and I'm going to try to find the public key, the private key on this system. So I'm looking for this public key. It's in the .ssh directory where you would expect it to be. But really, if you were sitting there and somebody had gotten onto your systems and they were looking for your private keys, you might want to know about that, right? So there's a rule for that. So if we go back and look at the logs, we're going to see warning. We have this grep private keys or password activities found. The user root, they did a find /root -name, blah, blah, blah. It was this process ID. It was on the host. The container ID was set to host. So I didn't do it in a container. I did it on the host. And the container name is set to host. If this was done in a container, then the container ID and the container name would be set, but they're not. They're set to host. So we know they weren't. All right. Chat window. Falco version, we're running an older version of Falco to make sure the labs work. The Falco version is 3.5.1. The most current version is 3.6.1, but we're doing 3.5.1 because we haven't had a chance to migrate the labs to the latest version. Okay, so I'm going to give you all 6 minutes to finish this on your own. And we will, I'll come back in 6 minutes. If you're done, take a quick break. Don't forget to hit the check button at the end of your lab. That'll take you into the next section, but only do this first one. We'll get to the other two. And then we'll jump back to the slides for a little bit. But like I said, I'll give you till, well, I guess, I'm sorry, I was looking at my wall clock, not my computer clock. My wall clock is off. I'll give you 4 minutes. We will rejoin at 1/4 to the hour. Okay. All right. So there were a couple questions in that lab, and I advanced my lab before how was the version requested in? I think that's the version of the Helm chart. Yeah, I know you see my screen. I was sharing it. But thank you. That's the version of the Helm chart. There was a couple questions at the end of that lab, and they were, if I recall correctly, because I already went past the lab, what driver are we using? And I don't, since we, well, if anybody saw it, you can put it in the chat. What driver are we using? I think was one of the questions. And then how would you change that driver? That requires some Googling. But if you look in the logs, you can see that in there. We're using the kernel module driver. Yes. So anyway, so let's go on here. So basically I kind of went into this a little bit, but I'm gonna go a little bit deeper. Falco is basically made up of 3 steps, right? We're going to grab some input, we're going to process it, and we're going to output it. Now, by default, we operate on Linux system calls. And so that was the kernel module driver is one way that we can pull system calls from the Linux kernel. For those of you who aren't familiar, system calls are basically the way you request any sort of resource from the operating system. So you may be writing a program, right? Python, whatever it is, and you're gonna be like open file. And there'll be a way to do that in Python, but whatever it is, that's ultimately going to be translated into an open system call. And that open system call is what every programming language that doesn't open ultimately ends up issuing that call, right? The system call. So open file, read file, close file, change, whatever it is, right? And so we take those system calls by default. Now we can also extend the input sources via our plugin architecture. So we have a plugin architecture that allows you to write custom plugins. So we have a plugin for Kubernetes audit logs. We have a plugin for Okta. We have a plugin for GitHub, CloudTrail, GCP. I think those are all of them right now. We like 5 of them. So now we can also, those event streams can be Linux system calls, and they could be these plugins. The thing that's interesting about system calls is if we go back and we look at this slide here, where was it? Boy, okay, maybe this next time I'll just put the slide up there. So if we look at the slide here, the reason that Falco works so well on both sort of natural hosts, like on a Linux host, as well inside of a container, is that the container and the host share the same kernel, right? So we're capturing system calls at the kernel level. And whatever's happening in those containers is getting routed through the container runtime into that same kernel. So everything that we get, all of the system calls that are being issued by the container, the applications of the container are all coming down into the spot where Falco has been instrumented. So that's why we work really well with the containers and Kubernetes. So, oh my goodness, next time I won't do that. All right, so the next step is process, and processing is actually the process is a two-step process. There's 2 distinct steps here. The first is enrich, and the second is actually, and they're backwards. The first is filter and then enrich. So we have 2 libraries in Falco. So Falco has sort of the kernel module, or it's basically the Falco driver, which can be a kernel module or an eBPF probe. And that's what's collecting the system call events. It's going to pass those into user space, and I'll talk about that in a second, where they will be filtered and enriched. And they're done by a couple of libraries called library SCAP and library SINS, for the library of system inspection and the library for system capture, right? And one of them grabs the events out of the kernel space and sort of bubbles them up where they get enriched, right? So an event comes in. Do we track that system call? Yes, we do. Does it violate a rule, or does it fire a rule? Yes, it does. Okay, now we need to enrich that. So the filtering is like, do we monitor that syscall? Do we trigger a rule? Yes, we did. Okay, let's enrich that. And enrichment is the process of taking system call output and creating something that is, human readable. So when, and I think I actually have slides on this, so I won't go too deep into it. Once you get an alert, that alert by default can be sent to the sort of standard Linux output areas, right? Standard out syslog can also be sent to gRPC and HTTPS endpoints where you can pick it up with, an application of your choice. And there is also another application called Sidekick that we'll talk about that extends the endpoints that Falco can deliver alerts to. But by default, what you just saw was system calls being processed and then sent to standard out. So this is a little bit more detailed. So as I mentioned, the kernel driver up here in the gray box, kernel module or eBPF probe, that operates in the kernel and it grabs system calls and it throws them on something called a ring buffer. The ring buffer can be sized so that, if you have a very busy system, you will want a bigger ring buffer. And we're just writing those events out to the ring buffer as they come in, right, with the kernel module or the kernel driver. And then on the other side, those libraries I mentioned, right, they're grabbing the events off of the ring buffer and they are processing them, right? So we kind of covered a lot of this already, but that's sort of the delineation between the user space and kernel space. And you'll see, the driver can be the kernel module or the eBPF probe. And we'll talk about what that means in another slide. We'll also talk about what this state engine and event enrichment means. So let's jump into that. So we don't have a slide on kernel modules, so let me talk about them. So if you want the kernel to do something specific for you, right? If you want the kernel to forward all of these system calls to this ring buffer, right? That's not something the kernel does by default. So there's like 3 ways you can make that happen. The first is you could go and you could rewrite the kernel, right? And you could put that functionality in the kernel, and then you could submit those changes to the governing board, Linux Foundation, the Open Software Foundation, or whoever it is, and say, I want to release a new version of the kernel with my changes in it. And then they could argue about it for 3 years and they can reject your submission and your changes will not be in the kernel, right? Because to change the kernel is a very, very, very high bar. So they said, well, we need to have some way for people to be able to modify kernel behavior without rewriting the whole kernel. So that's what kernel modules basically do. Kernel modules allow you to write code that executes in the kernel, and they can be loaded in, dynamically loaded in, loaded out. You do not need to recompile your kernel or anything like that. And they're, they've been around for a long time. And they're, so they've been around for a while. They're well documented. They get the job done. What's the risk? Well, you've introduced a piece of code into your kernel, and if something goes wrong with that code, it could corrupt the whole kernel and take your system down, right? We've been doing kernel modules for a long time. That, our kernel module, I think, is very tried and true, very trusted. I don't have any problems with it, but that is a limitation of kernel modules in general. Yeah, we'll cover that. That's a good question. Can filters and enrichments be populated with custom rules and beautifying components? We will cover that in the next slide or in a couple slides. So kernel modules, tried and true, been around for a while, could cause stability issues if they're not written appropriately. So what is the new hotness then? It's something called the extended Berkeley packet filter. So Berkeley packet filters were originally written as a way for to do like low level networking stuff in the kernel. Like, how can we filter out packets? Well, obviously packet filter. How can we filter packets? How can we do routing? How can we do, firewall rules, that sort of stuff? It has evolved to the point of it's just a way of extending the capability of the kernel in a more safe and efficient way, right? So there are features in eBPF that validate the code before it is executed. And that kernel modules don't do that. So eBPF probes, as they're called, when they're loaded, they're compiled. They use a just-in-time compiler to compile the code, and that code is, they're doing static analysis, runtime analysis on that code. They're looking at like, how deep do these, is there branching conditions? How deep do they go? Do they loop? Right. And you can only go so deep on nested branching branching statements. And we look at that, and then the code gets isolated when it's run. And so it allows us to get the benefits of implementing custom code, but done in a much more stable way. Now, why don't we just use the eBPF probe all the time? Well, it requires a fairly modern kernel, right? And so if you have a modern kernel, 5.18 or later, I believe, you can run eBPF, and it's a great way to do it. On some cloud providers, it's the only way to do it. And we have two versions of our eBPF probe, the classic and the modern. If you run the modern eBPF probe, we'll detect if it's already in Falco, and if you can run it, we'll just load it for you, right? The other thing with the kernel module that is a little bit cumbersome, not a little bit, it's a lot cumbersome, is that you need to compile that kernel module for every kernel out there, right? That's why we need the Linux system headers, and we will try to compile that driver for you. It doesn't always work, and so there can be some problems there. eBPF is a lot more generic, and hopefully in the ensuing years, it just becomes the de facto standard, and that's just the way we do everything. So, all right. So we talked about enrichment. To explain why enrichment is cool, I want to give you a high-level overview of how the Linux file system works. This is not like meant to be like the in-depth instruction into that. So we're gonna simplify some things, but basically this is how the Linux file system works. If I were to go out and issue the command cat/etc host, right? What happens there is one of the first things we're going to need to do is an open syscall on that file etc host. And so when that happens, you say open file name. And when that call returns, that open call returns, it returns something called a file descriptor, right? So never again do you ever use the file name, right? So if you need to read from that file or close that file, you say read 0 number of bytes, right? And the file descriptor is now the way you communicate with that file. And file descriptors are used as a proxy, if you will, for all kinds of different things: IP addresses, network sockets, any sort of input-output operation. A lot of them, they go through file descriptors, right? And then so when you open that file, you're going to read it. You're going to open it for read, write, read only. We're going to put that in a file table, and we're going to say, okay, well, that file was open for read. So file descriptor 0 is a read only file. And because if you did a cat, that's a read operation. And we're going to read etc host, and that the name of the file is stored in something called an inode table. So the file descriptor points at a file table, which points at an inode table, and it ties all those things together. There's no way to get from the file descriptor to the name of the file without traversing through those tables in the Linux file system, right? Which is kind of cumbersome. So that is why Falco implements something called a state table. So what we talked about, those two libraries, one of their jobs is to track the state of the system. So when the first fire up, the first library, SCAP, goes out and it audits the system, and it looks at procfs, it looks at the running processes, and it builds a state table. So let's say that I was running VI and I had a file open for editing, right? I was editing the etc password file or whatever, I don't know. It's going to go and be like, okay, that was process 475, and that's Mike, and that's file descriptor 4, and he's running VI on this, and it's creating state tables that include the, is this a read file, read write, read only, whatever? How is it, what were the permissions? What is it, a file directory, and what's the name of the file? How's that tied back to the file descriptor? And all of this is held in memory, because we want to be able, on subsequent operations, when we get a system call that says open 3, we don't want to give you an output message that said someone opened file 3. We want to say, hey, somebody opened the Etsy host file. And we do that by creating these state tables in memory that tie file descriptors to host names and don't require us to go back and traverse through all the Linux stuff to do that, because that would really degrade performance. So the enrichment process, so when first system is first booted up, we're going to do that inventory. We're going to create the state table. And then the other library, as events come in, it's going to process those events and update the state tables. So let's say I was running VI and I had a file open, and then it sees, so it goes out, builds a state table on that. And there's some reads and whatever. And then there's a close file descriptor 4. When Falco sees the close, it's going to go in and it's going to update the state table, and it's going to remove that entry so that it's not there anymore. So we're dynamically building and destroying this information in the state tables. And then, once we have built the initial version, we can then take over that way. And then if I do something after Falco's running, it's that second library season open, for instance, it would put another entry in the state table for that process or whatever, and then manage that, right? So that's what enrichment is. Can you add custom labels? So when we look at the rules, we're going to see that enrichment field. Enrichment fields can be added, but they're usually added via plugins. They're not able to be added just ad hoc, I don't believe. They're to be added as part of plugins, though, which we'll talk about in a little bit. So rules. So we have over 80 rules that we ship with Falco, that look at all kinds of different behaviors. People starting up certain programs, people accessing certain files, people doing certain things with containers, all of that stuff. Oh, let me go back one last thing on enrichment. We also get enrichment data, not just from the system call stream, but also from the container runtime and the Kubernetes logs. By processing those as well, that's where we get all the information about, like, the container ID, and how we can figure out what container ID maps to what container name and that sort of stuff. So enrichment includes the syscall data, container runtime data, and the Kubernetes logs. The rules, 80 of them. You can, of course, add your own rules. You can enable rules, disable rules, modify rules, create your own rules, whatever you want to do, right? Rules management is a critical part of running Falco in production, because without it, Falco can be fairly noisy, right? So, not fair, it can be really noisy. So you want to pick and choose what rules you implement and sort of filter out stuff you don't care about. Can you identify when a file is opened more than once and written over and over? I mean, you can definitely identify when a file's been opened. And so if you have something and you can identify when a file's been written to, so you could do that, and you can choose to implement rules on certain files. You'll see that in the rule section. So yeah, you can write a rule that would do that for you. Yeah, I think that would be, that'd be possible. Sure. So Falco rules. This is actually a rule. It's actually not a full rule, so I'm going to go back to the end. I keep meaning to move this slide up and I haven't done it. Or maybe, so this is a full rule here. So the rule has a name, terminal, shell, and container. It has a description. This is what you see, right? You see this description whenever it comes up. Actually, what you see is the output. Sorry, you don't see the description. This is the rule name. This is the description. These are the conditions. So every rule is just a set of Boolean operations. So was a process spawned? Was that process in a container? And was it a shell process? Right? Yes, yes, yes. Okay, we have triggered this rule. Yes, yes, no, we have not triggered this rule. If we trigger the rule, then we go out and we write this message. And these %user.name, %user.login UID, container.info, those are all those enrichment fields I mentioned. So they get pulled out of the state tables, and we can write them in here to make our output more readable. And then you notice in that first example I showed you way back when, we had a warning and a notice. There's like warning, notice, critical, error. There's maybe a couple more, but different priorities you can set. And then you can tag all your rules. So you can do filtering with them. After they come in, you can filter on different tags. So that's the structure of a rule. Now, we saw here this spawn process and container and shell proc. What exactly is that though, right? Well, those are macros, right? And so we have the idea of macros and we have the idea of lists. And macros are reusable bits of code. So rather than writing condition, if proc name in shell binaries and container.id did not equal host and event.type, blah, blah, you write all of that, writing all that out, we can create these aliases essentially, right? The macro is an alias. And now if you need to reuse that logic elsewhere in your rules file, you can, right? So in this case, right, shell procs means that proc name was in shell binaries. Well, what is shell binaries? That's an example of a list, right? So in our case, we have a list up here. It's just an array or a set or whatever you want to call it, a one-dimensional array of items, right? So strings. So in this case, we say like, oh, the process name in shell binaries, ash, bash, C shell, corn shell, sh, TC shell, Z shell, dash, whatever. That way, if you added a new shell or whatever, you could just update the shell binaries list, and that would, any rule that use shell binaries would just pull it from that list. Makes code maintenance way easier. So that's what macros and lists are as they relate to rules. So yeah, macros allow you to define conditions and reuse them, right? It's code reuse, and lists help you organize. So reduces complexity, makes it easier to extend rules and reuse them, and make, readability. So yeah. Okay. All right. Cool. All right. So now we're going to go back and we're going to do another lab. So let me go escape out of this and come back over here. Oh no. This bar up here is frustrating. Is that the one? I guess this is the one I want. Okay. So let's start this one. So we have a couple of different tabs here. We have this shell tab and this acid burn tab. And what we're going to do is we're going to simulate some attacks or suspicious behavior, and we're going to read those rules, and we're going to try to sort out what happened with each attack. I am not going to give you the answer to these right now. We'll come back. I want you to think about it, and then we'll come back to it. So we'll run through the lab so you can see how it works, and then we'll come back and discuss what each one did afterwards. So as we talked about, Falcos have rules and conditions. In this tab, we're going to basically just set up, use Kubernetes logs to just follow the logs interactively. So whenever we do something, a new entry will show up. Then we're going to come over here and we're going to run an attack. And you're going to see that this is a sensitive file open for reading by a non-trusted program. But what was really going on here, right? So I'm going to run the 3 attacks. Then I'm going to give you all some time to process these screens, and then we'll reconvene and we'll look at them. So this lab is basically just running attack 1, attack 2, and attack 3 is the bonus attack. Like Frankie Jonas, the bonus Jonas. All right, so we should have all that output here. We're going to, I've got 10, 11. So I'm going to give you all, yeah, I'll give you 9 minutes. We've got plenty of time. I'll give you 9 minutes to execute the attacks and then read through the questions for each attack, right? And try to really understand what's going on. I will tell you that the attack 3 attack 3 is super interesting. I think that's the one. Yeah, attack 3, only one person out of the hundreds of people I've done this workshop for has ever gotten the answer on how did we detect attack 3? Like, how did we, what in that rule tells us that it was a binary not part? How did we know that it was a binary not part of the base image? Okay, 8 minutes. We'll come back at 20 past the hour. And we will reconvene. Oh, sorry, my video was off. Okay, hold on. Had some stuff in the chat. No, man. You don't have to keep it down. Don't worry about it. No. Is there an easy way to version the macros? Not really. You can version rule sets, but there's no easy way within the rule set that I'm aware of to version like a macro. And it's like, it's either the entire rules file that gets versioned. What you can do, I guess, is you can have multiple rules files and you could version them by putting them in different files, but not really any more granular than that I'm aware of. And do not apologize for the questions. 100% okay. That's why we're here. Please keep them coming. I love it. All right. 7 minutes. We'll reconvene and we will take a look at what's going on. All right. Well, it's a little bit. It's like, I guess we still have a minute, but let's just jump back into it. So, I don't know. Does anybody want to unmute and explain what they think happened in attack one? If not, I can walk you through it, but I want to give somebody a chance if they want it. Okay, no worries. So we know, so we have a rule that says, hey, whenever a file, so we have a couple things going on here. We have a list of what we call trusted programs, right? And so anything that's not in that list is a non-trusted program. And so our case, the program that opened this was, it was actually a lot. Go ahead. Let's see chat. Okay, no worries. No worries. So, a lot of people say like, well, G Unicorn opened a file and it wasn't supposed to, and they opened the Etsy shadow. So the file that was accessed, the sensitive file was Etsy shadow, right? And at first glance, it looks like the program was G Unicorn. You would think, right? Program equals G Unicorn. But if you look at the command, really what was being run is a G Unicorn based app called app, right? So it's this application here that somebody ran that is probably your culprit. So what you'd want to do here, by looking at this, because the problem isn't with G Unicorn. Like G Unicorn is probably not what's causing you issues. G Unicorn wasn't accessing that file. It was this application. So you need to go to the developer, right? If you assume that's an internally based app, you'd be like, why are you doing this? Like, you shouldn't be doing it, or we need to have a good reason. And if you have a good reason, then you could just add that application to your trusted programs list, right? So you either, shut the app down, update the list, or fix the app. So pretty simple there. Error, package management launched in a container. So this one's pretty obvious, right? So, going back to the first one just for a minute. Yeah. So, what happened there may or may not have been a problem, right? It may just have been that, this app has a legitimate reason for reading Etsy shadow. We just weren't aware of it. It hadn't gone through security audit yet or something, right? And Falco caught it. So, may or may not be a problem. Just like this next one may or may not be a problem. Somebody launched a package management process in a container. So they went into a container and they ran APK add. All right. Well, so at level 1, this is an operational anti-pattern. In production, you should never be installing software into running containers, right? Like, that's just not what we do. What we do is we update the container image and redeploy the container and take the old one out of commission. So, best case scenario, somebody is taking a shortcut that they shouldn't take, and we need to educate them as to why that's a bad idea, right? But wait a minute, what did they add? Well, they added Nmap and OpenSSH. Okay, this could be problematic, right? Those applications in and of themselves may indicate that somebody's trying to find a way to, what's running on the system, or open up a back door with SSH. They're like, there's all kinds of things that they could be trying to do here. And you would be like, wait a minute, that is not, this takes us from like, oh, okay, this is a bad operational practice, to, no, it looks like someone's doing something they really, really, really shouldn't be doing, right? So that's what's going on here. Again, we are using a macro because we have this thing, package management process. So in this one, the rule would be like process launched in a container, package management process. There's going to be a list of those package management package managers, right? APK, geez, I can't even think today. APT, RPM, whatever it is. Yeah, there would be so wouldn't there be isn't a red flag that they were in as root? Well, so when you shell into a container, your container should not run as root. A lot of people don't fix that. So that is its own thing. there probably is a rule for container run as root. So they just shelled in and were operating as the user, right, in the container, right? So in this case, the container was root. But the idea that they shelled into a running container, that's also another rule that would have been violated, right? If someone shells into a container, you do not have to shell into it. You don't have to run a shell. Like you don't have to do an interactive shell to run a command though, right? So they could just do the exact shell, run this command. So that's a little bit different, but yeah, but yes, both those things are, running a shell into a container is also something that we alert on. Okay, so this last one, this one's a little bit more complex on what happened. So file below known binary directory renamed or removed, right? So what they did is they ran a command where they tried to go in and rename nmap to app, right? So they took user bin nmap and they tried to run it, rename it to app. And because maybe app is a trusted program, and if app was running, none of your systems would detect that because not a big deal, right? Like it's app, it's supposed to be running. But it's the step that happened before that, right? So we were talking about like, what's the suspicious behavior? And it's that somebody went in and renamed a file in a container, right? Which they shouldn't have done, right? So they somehow they got that nmap installed, right? They did that in the previous step, right? They installed nmap with APK, and then the next step they went and renamed nmap to app because app's running on your system. And then they ran it, right? They renamed it and they ran it. And they said, command app, scan the ports on appdb on this container and use this executable. Well, we know that this executable was actually nmap because in the previous step, we know they renamed it. Could you add a hash to each binary in the binary list in the rule? No, the rule is based only on the file name. So yeah, there's no hashes involved because hash is usually how people answer my next question. It's like, well, how did we know that this executable was not part of the base image, right? How do we know that? They're just running this thing called app. Was an app in the base image? How do we know that this wasn't the normal app? Right? If there was already something called app on that system and it was part of the base image and they just renamed something, but we already expected app to be there, like, how do we know it's not part of the base image? Well, to work through that, you have to think about how containers are built. So containers are built from what's called a container image. And container images are comprised of layers. So when you build a container image, and I'm going to just use the sort of canonical example, using Docker build, and you have a Docker file, you'll say from Ubuntu, apt install, httpd, right? Copy my HTML files to web root, and then expose port 80 and run httpd, right? And each one of those activities creates a layer, right? Each one of those steps. So that's a container image. They're read only with a bunch of layers. The difference between an image and a running container is that when you run a container, you add a read-write layer to the top of that container. And anything that changes in the container gets written into that topmost layer. So if you have log files, for instance, they would be written into the very top layer of the file. If you added a new file to the image, it would be written to that topmost layer, right? The file systems being used by container images are something called overlay file systems, and they basically stack on top of each other. And that's why the topmost layer always wins. So in our case, they went and they renamed a file, which created a new version of the file, which put it in the top layer. And if you look at the if you look at these flags, XC upper layer tells us that this was executed out of the upper layer of the container. And that's how we know that it was not part of the base container image. So any binary called app would be okay though, right? Yes, right, exactly. So if it's a trusted program and they rename it, right, that app would be trusted. What you have to do is you have to catch the operation before that, right? So by catching the operation before it, you see they renamed it, and then it's in a container. It wouldn't be running out of the normal image layer, it'd be running out of the top layer. So it's those type of things that allow you, and that's why I go so deep into this last example, because you have to start thinking about, what am I really looking for, and how can I find it, right? And this is an example of a very creative way of detecting like an anomaly, right? Without having to have file hashes and lists of all the files that were part of the base image and all of that. We can do it by like sort of just saying, well, what's the behavior of a container? Anyway, all right, so that is that lab. Let's go in now and set up our last lab. And talk a little bit about the Falco ecosystem. So we have been working with system calls. We have been seeing the output by looking at the Kubernetes logs for the Falco pod. That is not sustainable, right? You can't, one, system calls are great. You could do a lot with just system calls, but the output mechanism does not work. We talked a little bit about the plugins. So plugins augment system calls by looking at other sources like Kubernetes audit logs, Okta logs, CloudTrail logs, GitHub, for all these other sort of activities that expand beyond just interacting with containers. The output side of it, if you recall, I said that one of the endpoints for Falco by default was an HTTPS endpoint. Falco Sidekick is a companion product, a sidekick, if you will, that attaches to that endpoint and allows those events to be forwarded to, I think at this count, 60 different endpoints, 5 dozen different endpoints. So with Sidekick, you can take events and move them into other systems. Now, I will say, only one person has ever answered that one question about the container writable layer. Hold on just a second. Is there a plugin that would tell? Well, there is not one. Well, it depends, right? There isn't probably one that would, if that showed up in an AWS CloudTrail log, then we could do it with the plugins that we have. If not, you would need to write a plugin for that database. If that activity is emitted out to a log for that database, then a plugin can be written to capture that event. Does one exist? The only thing I can think of is if that event is caught by AWS CloudTrail, then the CloudTrail audit log would catch it. But you would still have to, again, you'd have to you could, but you'd have to write the plugin for the database logs is what I'm saying, right? So if the database logs existed, so let's say it's Mongo, right? Well, yeah, let's say it's Mongo or it doesn't even matter. It's MySQL, whatever it is. You would have to write a MySQL plugin that reads the MySQL logs and emits them to Falco. So does one exist? No, but could one exist? Absolutely. If that information is in the environment. So is there for those not reading the chat, is there a plugin that can tell when a field is selected from a table in a database, or is that too high level? The plugin does not exist, but I am 99% sure a plugin could be written. So why are we doing this? Let's close this back up. So I will say though, the one question, and you've been asking some great questions. The one question that's been asked every workshop I've ever done has not been asked today. And that question is, but what do you do once you've been alerted? Right? You know what I mean? Like when I order I don't go to a restaurant and order spaghetti, right? I order spaghetti and meatballs, right? I don't make a peanut butter sandwich. I make a peanut butter and jelly sandwich. I don't want to just detect threats. I want to respond to them, right? I want detection and response. And so people are like, well, does Falco do response? And the answer is not out of the box. That's what Sidekick enables, right? Sidekick allows these events to be emitted to systems that you already have in your environment, where you can then take action. So we can send it to chat programs, to logging programs, to message queues, to functions as a service platforms, to metrics, to alerting platforms, to storage, whatever you want it to be. You can write it out to an S3 bucket. You can send it to a queue, and then it gets pulled off the queue by something. And then it, I think we kind of talked about that here, right? This is where you can start reacting to events. So for instance, let's say that somebody ran the package manager inside the container. The package manager, that alert would come up, right? And you'd be like, okay, so what am I going to do with it? Well, one thing you might do is you might say, all right, well, that's, if that alert happens, I want to forward that to Lambda. I want to take that container. I want to relabel it so it gets put out of commission. And when it gets pulled out of the deployment, Kubernetes will fire up a new one. So you could write a little function to do that. Function would probably be like 10 lines long to do that. Right? So that's the kind of thing you can write. Yeah, exactly. So Falco allows the whole solution to be more than forensic, but actual live reaction. Yes. Falco takes you from being detection and notification to detection and potentially reaction, right? But that you write that reaction. And some people just send it into their security event management systems or whatever they want to do. Sidekick can be installed alongside Falco when you install it, or Sidekick can be installed as its own thing. The typical pattern that we see with Sidekick is fan in, fan out. So you'll have multiple Falco instances going to a single Sidekick instance. That Sidekick instance fanning output to multiple different endpoints. So that, standalone Sidekick install, and then different Falcos that connect to it. We have in our lab, you're going to see a tool called Event Generator. This is another thing people often ask. They're like, well, how do I know that my rules are working? Event Generator does a bunch of different rules, different events randomly. It allows you to test those rules. Do not run this on a production system, right? If you do, run it in a container, because it's going to modify. If you ran this on the host, it's going to do things to the host you probably don't want it to do. So run it in a container, right? Or run it in a pod. Do not run it on your system, on your host by itself. Yeah, Falco is the camera and Sidekick is the person watching the screen. That's a really good analogy. Falco is sort of detecting what's going on. And then, yes, the Sidekick is like the guard sitting at the thing saying, oh, yeah, that alarm always goes off. There's a loose wire. I'm not worried about it. Or, oh, that door should never be open, and this is critical. I need to call somebody right now. All right, so we are in our last lab. I didn't hit check, but let's hit check and move on to our last lab. So our last lab actually uses, I have to fire up, where is it? I have to fire up Slack. So what we're going to do in this lab is we're going to install Sidekick, and we're going to link it to Slack. We're going to use Slack's webhook URL feature, or Sidekick's Slack webhook URL configuration entry parameter to give it a webhook for Slack, and that will send the notifications over there. So the first thing we need to do is we need to go ahead and install Sidekick. But when you do, no, sorry, wrong one. Control C, clear. Want this one. When you do this for yourself, you want to change this last field down here to your name or something. It doesn't matter. You can put whatever you want in here. I'll just put in Mike G. Coleman because this is all getting written to the same Slack channel. And if you don't change that, then you won't really know what notification is yours. So I'm going to go ahead and install Sidekick. And we'll wait for it to spin up. So Falco is up and running, but Sidekick, actually, let me do this. kubectl, get pods, namespace Falco. Oh. Geez, I can't type today. kubectl, get pods, and Falco. There we go. All right. So just show you this. Like, so Sidekick is made up of a Redis database is where metrics get written. So Sidekick collects its own metrics on what rules have been fired, that sort of stuff. And then there's a UI that goes with it that's very rudimentary. And then of course there's a Falco pod. So we're restarting the Falco pods. We're installing the Falco Sidekick daemon. We're installing the Redis server, and we're installing the UI, which is a little web server that serves up stuff for us. So it looks like everything, we got at least one instance of everything running. So we should be able to get the Sidekick UI. So we need to run this no hang up and do a port redirection because of the environment we're in, so that we can we're port forwarding our internal IP address to an external IP address of the virtual machine so that we can see the UI. So here it is. And here's that UI, right? And right now there's nothing going on because we haven't run anything, right? So let's go ahead and test the deployment. So we're going to go back here into acid burn. And oh, actually, we want to do this. We do it over here, I think. I'm going to do Control V. And now if we go back, I shelled in to the Redis container. So, you know, you were asking earlier about like, oh, you know, that wouldn't being root be a problem? Well, to be root, you'd have to shell in. And if we go, not here, if we go here, you can see in the events tab, we did get a warning that a shell was spawned in the container, right? So, and it was, you know, with a terminal attached. So that would be the first thing that would have been, had to have happened before any of that other stuff we saw when I was in the previous sections. All right, so that is that one. And you can see that in the Sidekick UI. Let's go back and run attack 3. And the one thing I neglected to point out, oh, not here, here. Let's get out of here. And let's go there. Let's do this. There's also this Falco Sidekick config minimum priority critical. We're only going to see critical error or critical alerts fired off into Slack. We're not going to see all of them. We're only going to see the critical ones. So that's why if we go into the Sidekick UI, we will see a bunch of stuff written out here, but only one of them is critical. One of it is an error, and that's the drop and execute a new binary, right? That one we saw before, that's actually critical. And so that should show up in our Slack channel. So if I go into Slack and I go into Falco notifications and I say Mike G. Coleman, and oh, sorry, that's not, I did the wrong thing. Mike G. Coleman. And we look, is that, yeah, that's 10:42 a.m. my time. Yeah, so that's from today. So that is the notification that just came through on that. Yeah, 10/23/2023 at 1742 UTC, which is 10:44 a.m. local time for me. That's why it's 10:44 a.m. up here and 7:42 there, because that's the UTC. Anyway, so that is the events being forwarded to Slack. So that's a very rudimentary use case of Sidekick. Critical alerts get sent to Slack. Does the root shell closing trigger? Can you post you? Oh shoot! Yeah, you guys need the invite to the Slack channel. Sorry, my bad. Yes, I will. I will do that. It should be in the slides. Let me go back and find it. Boom, boom, boom. Let me close this. Where is the invite code? Oh shoot! All right, now I gotta go. I don't know how to get the invite code. So this is embarrassing. All right, well, so this is embarrassing, and we'll figure it out. But because this happened, you get to see what happens when so I'm never embarrassed by demo failures, because this right here, we got to, I'm on the, I'm not on my personal one. I'm on my, let's skip this in 1 second. So this is, I'm going to,
We're on the 4th floor of the Westin Hotel, the Grand.
So that is me, and that is Bill Gates, and I'm doing a demo on stage, and an earthquake happens. So me not knowing the Slack invite URL doesn't faze me, because I've done a demo on stage with Bill Gates during an earthquake. Anyway, you can go to me and Bill Gates at earthquake on the internet, and it's there forever. All right. So anyway, all right, let's go back to the chat. Dot earthquake. Anyway, okay. So, yeah, I don't know. Trust me, it's going to work for you. You saw it work for me. All right. So let's go back real quick. I'll give you guys, I'm going to look for that. I'll see if I can find it. You guys run through the lab. We'll reconvene in 8 minutes and do a 5-minute wrap up. So I'm going to pause my stuff, and I'll be back in 8 minutes, let you guys finish the lab, and then we'll do a wrap up in 5 minutes. I just realized that we didn't do the event generator part. So that super simple. You just come in and you run it, like I said, run it in a container. It'll pull that down. Oh, that thing I talked about, layers. Each one of these, that's a container layer. Like that's how it manifests itself when it pulls itself down. Okay, so it's running now. And if we go into Falco Sidekick UI, you should see like many more events being generated in the UI, and like a deal. Here's a debug shell. There was a debug shell. If you go to the dashboard, you'll see a lot more different type of errors and data there. So that is just the event generator. So I didn't show that before, so I just wanted to make sure I came back and show it. So we will reconvene on this in another 4 minutes. So the wording after a few seconds, they're going to start monitoring your containers, looking for security issues, is kind of misleading. It will not identify any existing security issues but identify security issues happening from the launch. Yeah, I mean it's so there's and then AI Camp said has to do with runtime security and any issue with the containers as such. We can try using image scan and vulnerability scan to identify problems. One of the slides that I blew by and I didn't really touch on was this idea of where does Falco sit into an overall security landscape, right? So there's this idea of shift left and shield right. And so this idea of image scanning and vulnerability scanning and all of that stuff and secure software supply chain and making sure that all your dependencies and everything are taken care of. As you build and deploy software, that shift left, right? Super important. What Falco deals with is what happens after it's running in production. Now, certainly, if events happened and Falco wasn't running, we're not going to detect them. The other thing we don't really do is we don't look and say, oh, look, you're running this version of the software. You know, what we look at is the behaviors of what's going on. So I did there's a CNCF webinar that I did that should be up on YouTube. I'll see if I can find it. And it was sort of going down this path, which was that was like, yeah, so we're not looking for security issue, we're looking for behavior, right? We're looking for behavior and anti-patterns that may or may not be security issues, right? In some cases, like, and that the thing, security issues is like so broad that I can see where you would look at that and go, that's a little over promising, right? So note taken and basically in agreement with you on that. So, all right, well, let's get back to the slides. We are almost out of time here, but we want to wrap up here. And I want to thank you. First, I want to thank AI Camp for hosting us. I want to thank all you for attending for the session today and the questions and whatnot. You know, and kind of what we were just talking to, right? This idea is like what we're about with Falco is, you know, looking for patterns and behavior that are indicative of things that you should be aware of, right? Either operational anti-patterns or genuinely nefarious behavior. That's what Falco is about. And just making sure people aren't doing stuff on your hosts or your clusters they shouldn't be doing. At its core, you know, Falco is comprised of a kernel driver in kernel space, which is the kernel module or eBPF probe. And then up in the user space, we got a couple of libraries that grab events and filter them and enrich them and send them out. Falco rules, pretty straightforward. They're Boolean expressions. They can be extended by rules and macros. You can set different priorities on them, and you can use tags to filter them out. Yeah, if you go into your Falco UI, Falco Sidekick UI, you can see the tags on those things. You can click them and use those to filter some of the responses out just to see that in action. Falco is great on its own, but it's even better as part of a larger ecosystem. You know, bringing in plugins to extend input sources and then using Sidekick to extend output destinations. There is a great book out there, Cloud Native Security with Falco from O'Reilly. There's also the falco.org website. Both are outstanding resources for you. If you'd like to get more involved with the Falco community, every Wednesday at 4 o'clock UTC, which is 9 a.m. Pacific, we host a community call on Zoom. Sometimes they're an hour and sometimes they're 5 minutes. Just depends on what the community needs. So, you know, check that out. You can reach us there. We also are, we have a Slack channel, a Falco Slack channel on the Kubernetes Slack server. So if you go to kubernetes.slack.io, I think, Falco on that. So, all right, let's see here. All right. If a rule is modified, is there a way to see which version, even if the rules file version is executed? There's only rules. There's only ever going to be one instance of a rule, right? So if you have a multiple rules files that you're loading, there's only one version of a rule. So, and it's going to be the last one loaded. They're ordered in hierarchy. If a rule is modified, is there a way to see which version? I mean, if a macro is modified, no, I don't think there is. There's no way to kind of track that. All right. Well, we are at time. Thanks everybody for joining. Thank you, AI Camp, for all of it. You know, hope to see you down the road in the future. Join us on the Slack channel. Check out the community call. We'd love to have you involved. We're a fully open source project, so we're always looking for new contributors, maintainers, and all that stuff. So with that, have a great rest of your week. And thanks for spending time with us today.
Thanks, Mike. That was an excellent workshop. I'm sure participants have enjoyed and learned the runtime security. So participants who are completing the workshop can feel free to email info@aicamp.ai and claim their certificates of completion of the workshop. And yes, thank you for being a wonderful audience today and for interesting questions to Mike today. I hope to see you all again in another event of virtual series from AI Camp. Thank you and have a nice day. Thanks, Mike, for joining us and hope to see you work with you alongside.
All right. Take care. Bye-bye.
Take care. Bye-bye.